Hi, thanks for joining me today. I'm going to be showing you a cool sort of summation of trigonometric functions result. This was shared to me by somebody called Dennis Gittinger, who got in contact with me through email. Apologies if I've pronounced that surname wrong. I'm not sure how you pronounce it, but Dennis Gittinger, I'm not sure. So I hope you're watching, and thank you for the result. If you guys ever want to share some cool maths results you've seen or some cool maths problems or something you want to see on my channel, just email me. I'll leave my email in the description below in this video, and I'll probably just keep it there for all my future videos as well. And it's also, if you're on desktop, you can find my email on the channel about section, if you're subscribed, I think. Anyway, let's just get stuck into what I'm going to be doing today. I'm going to be proving this result, that the sum from k equals 1 to n minus 1 over 2 of cosine of 2k pi over n is equal to minus a half. And that's for any odd n bigger than or equal to 3. Okay, which is kind of cool because it kind of seems like this left-hand side here would depend on n, but we're going to show that it's independent of n and just equals this constant minus a half. Let's get stuck into the proof. Okay, so the way we're going to prove this result is just sort of a direct proof. We're going to start from the left-hand side, do some algebraic sort of manipulations and calculations, and show that it equals minus a half. Okay, so we're going to start from the left-hand side, which is this thing here. And what we're going to do is straight away use Euler's formula. So that says that e to the I theta is the same as cosine theta plus I sine theta. Now, I've already made 2 videos in which I prove this result, and they're both actually non-standard proofs. So if you haven't seen them, I recommend that you do, even if you know Euler's formula, because those proofs are pretty cool. I'll leave links to both those videos in the description below, but I'm not going to be proving it in this video. But that basically means that we can write, because the argument theta in this case is just 2k pi over n, which is real, that means that the cosine of 2k pi over n is just the real part of e to the I 2k pi over n. So I can just write this thing here as the sum from k equals 1 now to n minus 1 over 2 of the real part of e to the I times 2k pi over n. But here I'm just summing up the real parts of a bunch of complex numbers, but that's the same thing as just summing up those complex numbers and then taking the real part. So I can just bring this real outside of the summation. So it's the sum from k, the real part of the sum from k equals 1 now to n minus 1 over 2 of e to the I. Now we've got 2k pi over n, but I'm going to write this as e to the I 2 pi over n raised to the power of k. And the reason for that is now if we just look at this thing here, we see that it's a geometric sort of series or geometric progression, because the sort of first term when k is 1 is just e to the I 2 pi over n. The next term when we have k equals 2 is this thing here but squared, then cubed, then to the power 4 and so on, all the way up to n minus 1 over 2. Now I can actually never remember the formula for a geometric progression, so let's just quickly derive it. If we have s being r plus r squared plus r cubed plus dot 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 all the way up to r to the, let's use t, where t is a positive integer, and r is not equal to 1, then we get that r times s is equal to, r times r gives us r squared times r squared gives us r cubed, and so on. Then r to the t minus 1 is going to give us an r to the t, but then r to the t times r is going to give us an r to the t plus 1. So squeeze it on there. Anyway, subtract, doing this line minus this line gives us that s minus rs is equal to r minus 0, which is r, then the r squareds cancel, the r cubed cancel, and so on. I'm sure you've seen this before. R to the t minus r to the t is 0, and the last term is just r to the t plus 1. So we're going to take off an r to the t plus 1 like so. Then just dividing both sides by 1 minus r, or I guess factorising this left-hand side first as s times 1 minus r, then dividing through by 1 minus r, which is fine because r is not equal to 1. We then get that s is equal to r minus r to the t plus 1 all over 1 minus r, like so. Now in this case we have that r is equal to e to the I 2 pi over n, and this does not equal 1 because n is not 1. We're assuming, remember, n is at least 3, so that means this guy here is certainly not equal to 1. So we can apply sort of this argument, and we get that this is equal to the real part now, and we have r is equal to e to the I 2 pi over n, and t is equal to n minus 1 over 2, so just directly plugging in this guy here, we're going to get the real part of e to the I pi, e to the 2i pi over n, and that's r, minus e to the I 2 pi over n, now raised to the t plus 1, but t is not n minus 1 over 2, so t plus 1 is n plus 1 over 2, so it's this guy here raised to the n plus 1 over 2, and we're dividing that by 1 minus r, which is 1 minus e to the I times 2 pi over n, like so. So now we've got something which is sort of a closed form. There's no more summation, and we want to take the real part of it. So you might just go straight into multiplying by the complex conjugate and using Euler's formula first, then multiplying the denominator by the complex conjugate and getting something. But we can actually use a few shortcuts to simplify this first to make our job a lot easier. Let me clean the whiteboard and we'll continue. Okay, so we just proved that this guy holds true. The sum from k equals 1 to n minus 1 over 2 of cosine of 2k pi over n is equal to the real part of this thing here, e to the I 2 pi over n minus e to the I 2 pi over n to the power of n plus 1 over 2, and then divided by 1 minus e to the I 2 pi over n. Okay, what we want to do is perhaps simplify this right-hand side. So what I'm going to do first is look at the denominator, and I'm going to complete the square. Sorry, not complete the square, look at the difference of two squares. Because if we look at this thing here, e to the I 2 pi over n as e to the I pi over n all squared, we can then write this denominator as just 1 plus e to the I pi over n, and then 1 minus e to the I pi over n, like so. And now this numerator here, we've got this term here which looks kind of ugly, but we can do some simplifications on it. Let me just write out that term here. We've got e to the I 2 pi over n, and then we're raising that to the n plus 1 over 2. That's the same as using our exponent rules, just multiplying this thing here by n plus 1 over 2. Now clearly the 2's are going to cancel, like so. So what I'm left with is e to the I pi times n plus 1 over n plus 1. But then I can write this as e to the I pi times n over n times e to the I pi times 1 over n. Because obviously this thing here I can just bring together by using exponent rules and then adding the exponents together, and that's going to give me this thing here. But n over n is just 1, of course. So this thing is just e to the I pi, and e to the I pi, we know just using Euler's formula, is just minus 1. So this altogether is just equal to minus e to the I pi over n. So we can replace this whole junk here with minus e to the I pi over n, and this minus sign is going to cancel with this minus sign. So all in all, this thing here becomes the real part of e to the I 2 pi over n plus e to the I pi over n, and then we're dividing that by 1 plus e to the I pi over n, 1 minus e to the I pi over n, like so. But from the top here, we can actually factor out an e to the I pi over n, and what we'll be left with is e to the I pi over n plus 1, which will cancel with this thing here. Hopefully you can see that. So what we're left with is just the real part of e to the I pi over n divided by 1 minus e to the I pi over n, like so. Okay, so we started off with this horrible looking expression here, and we've just used some simple algebra to bring it down to this guy here. And now we're going to have to use Euler's formula to be able to evaluate this. So if I maybe clear up some space here and write this now as the real part of the numerator is just cos pi over n plus I sine pi over n. And the denominator is just 1 minus cos pi over n minus I sine pi over n. So 1 minus cos pi over n, like so. That's the real part. Then minus I sine pi over n. Now to work out the real part of this, we're going to have to write this in the form a plus bi, where a and b are real. So we're going to have to multiply the denominator and the numerator by the complex conjugate of the denominator. So on the top then, we're going to get 1 minus cos pi over n plus I sine pi over n times this guy here. And on the bottom, we're just going to get a real quantity. Anyway, I've run out of space at the bottom of this whiteboard here, so let me clear up the whiteboard and we'll continue, and we're pretty much almost done in proving the result. Okay, so we're at the final step now. We've shown that the summation we're trying to evaluate is equal to the real part of cos pi n plus I sine pi over n divided by 1 minus cos pi over n minus I sine pi over n. And as I said, we're going to multiply the top and bottom by the complex conjugate of the denominator here. So this is equal to the real part of cos pi over n plus I sine pi over n times the complex conjugate of this guy here. So that's just 1 minus cos pi over n, and then we're going to flip the sign here, so it's plus I sine of pi over n, like so. And on the denominator now, we're going to get this guy here multiplied by its complex conjugate. But remember, a complex number z multiplied by its complex conjugate, z bar. Z times z bar is just the magnitude of z all squared, which is just the real part squared plus the imaginary part squared. So this on the denominator is just 1 minus cos pi over n all squared plus sine squared of pi over n, like so. Okay, now remember we're only really interested in the real part, so the imaginary part from the numerator, because now the denominator is just real, the imaginary part from the numerator we can just ignore, and we can get rid of this real sign by just considering the real of the numerator. Well, how are we going to get a real on the numerator? Well, we get 1 from cos pi over n times 1 minus cos pi over n, and we're going to get another real from I sine pi over n times I sine pi over n. So this thing, all in all, is just equal to cos pi over n times 1 minus cos pi over n, which is just cos pi over n minus cos squared pi over n. And then I sine pi over n times I sine pi over n is minus sine squared pi over n. And hopefully you can see something. This guy here, minus cos squared minus sine squared is just 1, or sorry, minus 1, because obviously I can factor out a minus 1 from this, and I get cos squared plus sine squared, which is identically 1. Anyway, that's on the numerator. And on the denominator, if I expand this out, I'm going to get a 1 minus 2 cos pi n plus cosine squared pi over n. But then adding on cosine squared pi over n with sine squared pi over n is going to give me another 1. So on the bottom, I'm left with 1 plus 1 minus 2 cos pi over n, which is just 2 minus 2 cos pi over n. So that's, if I factor out the 2, 1 minus cos pi over n. Yeah, so just going from there to there, if you're unconvinced by this, just do it on a scrap piece of paper. I'm just doing it in a few steps because there's not much space left. Anyway, on the top, as I said, minus cos squared pi over n minus sine squared pi over n is just minus 1. Like so. So on the top, we've got cos pi n minus 1. And on the bottom, we've got 1 minus cos pi over 1. But I can perhaps write this now as minus 1 plus cos pi over 1 and bring a minus 1 at the front. So this guy here is going to cancel with this guy here. Cos pi n minus 1 is going to cancel with the minus 1 plus cos pi over n. So all we're left with is 1 over minus 2, which is just minus 1 over 2. So minus a half. And that proves the result, that when you're summing up these cosines, cosine of 2k pi over n, where n is an odd integer bigger than or equal to 3, and you're sort of summing up to the midpoint, you're always going to get minus a half, which is a pretty cool result. If anyone knows any sort of geometric explanation for this, I'd love to see. But yeah, this is an algebraic proof of that pretty cool result. Anyway, thanks for watching, and as always, if you do want to share with me some cool results or cool problems you've seen, email me and I'll be more than happy to have a go at them. And yeah, that's all for now. I'll catch you in the next one. Have a great day.